Okay, let's get started. So the last time we're doing worksheets. We are doing worksheet 7, and one of the questions there, this one. What are the updated equations for double expected SARSA with an epsilon greedy target policy? Okay, let me record it. Double expected SARSA epsilon greedy. Okay. What's the update equation? And we started to discuss double Q learning because we need to apply the idea underneath double Q learning to expected SARSA. So the ingredients here are something like this double learning or whatnot. Specifically in Q learning, how does this work? And then the ingredient is going to be expected SARSA. We have to recall what that was. But we talked about that a lot. And epsilon greedy targets. Right. Double Q learning. I first simplified the setting to the bandit setting. So we were just talking about that you're in a bandit problem. You have K actions or K arms. You observe the rewards from these arms after pulling them a number of times. Maybe you estimated the average reward for each of these arms. And then your job is to estimate the maximum expected reward, the best expected reward that you can expect from this bandit. And then the question was, how would you do it? So let's write this down formally again. So maybe the simplest setting that you can imagine is that you have these K arms. And the distributions for arm 1, arm 2, and so on and so forth, let's say they are normal, where U1, UK are real numbers. So these are the reward distributions. So for arms 1 to K, these are the distributions from which you're going to see the rewards. You don't know the mean. You're going to see a bunch of rewards from them. So maybe one simple setting would be that you pull each arm n times. And you see n rewards from the respective distribution. Again, I is between 1 and K. Question? Okay. And the task is to return an estimate of the maximum reward It's not the usual task in Bennett. It's not the usual thing to do to ask the question, what's the maximum reward? We usually ask the question, which arm to pull? This is asking, okay, but fine, but how much reward do you expect to get? So it's an interesting question. And the simplest possible approach in this case would be what? It would be to calculate a mean for each of the arms. Okay. So just a sample mean. And then just return the maximum. Of these. Okay. So that would be one way of doing things. So if we do this, what is the distribution of x bar of I, the average of the rewards that I receive for arm I? You know what the distribution of that is going to be? We studied these normal distributions. We're taking averages. What are we going to end up with? You start with normal. You add normally distributed random variables. What do you get? Normals. Okay. So the average is also going to be normally distributed. Normally distributed random variable can be described exactly by two parameters. What are those? Mean and variance. Okay. So what is going to be the mean of x bar I? Same as what? Mu I. Okay. So expected value of x bar I is mu I. What's the variance of x bar I? That's the other parameter that we need to fully know the distribution of x bar I. Well, we started with 1, but we took an average of n values sampled from this. Do you expect the variance is the same as like if we just have one observation? 1 over something. 1 over what? Yeah, it's like variance or standard deviation. We are doing variance here. Right. So if the mean was 0, then the variance would reduce to just the expected value of the square of x bar I. You have all these products, cross products. Their means are 0. And the cross products in independence, we had independence, they go away. And you get 1 over n squared because we were squaring. And then you add up n times 1 because you have xi squared, xij squared, an expectation. That's just 1. So you get variance because of independence. Did I say that they were independent? They're always independent. Yeah. This is IID. So the variance is going to be 1 over n. Standard deviation is, the variance is like, okay, like you have to take the square root of it to kind of see the scale. So that's 1 over square root, and that's what you were remembering. Okay, so we can also summarize this by just saying that we have this random variable which is sampled from a normal distribution with mean mu y and variance 1 over n. Okay. So n, we have k of these, we take the max. So one special case is when mu1 and mu k are all equal. That's kind of like a nice special case. That will tell us quite a bit about how this estimate behaves. If we are in this special case, and we can draw what this, how the situation looks like. So you just have this common mean. It's called mu star, the same as mu1, same as mu k. And you were sampling k distributions from this Gaussian, whose standard deviation is 1 over square root n. So there will be, you know, points here, points here, points here, points there, and so on and so forth. The larger k is, the more spread out these points are going to be, right? Like, if you take the largest of these points, the further away it is going to be from mu star to the right. And so if we thinking about, okay, how big this could be compared to mu star, so let's call it mu head of k because we have k arms. So expect this to be large and actually go to maybe infinity as k goes to infinity. Should be increasing with k, right? It turns out that people do study this behavior as k gets really large, and you get a very nice, precise formula that tells you how large this is going to be. So this deviation is also dependent on square root n. And so as n gets large, it gets much smaller. If we want to get back to when the standard deviation is just 1, we should multiply this difference by square root n, then we kind of scale back everything. So after you do that, you are in the kind of the standard case. So you take expected value of square root n times mu hat k minus mu star. And it turns out that if you divide this by square root 2 log k, you take the limits, as k goes to infinity, you get 1. So in a way, you can say that the expected value of this normalized deviation, you expect it to be close to square root log k, in the sense that as k goes to large, they go to infinity at the same rate. So if you would plot these two curves, on the left-hand side, you have this quantity. On the right-hand side, you have this quantity. They would asymptote to each other. They would both go to infinity, and they go to infinity exactly like this. That's what this means. Because I chose so. Because this is a simple case. But in this case, we can at least understand what's going on. If you're interested in some more complicated cases, you can look into that. But this is a very clean, very simple case where we have a chance to understand what's going on. So going back to the question of like how much bias do we expect to see in this case, I can divide by the square root n, move it to the other side. Then I see that this is the bias that I expect to see. It's basically log k over n under the root. So the larger the k is, the larger the bias is going to be. It's growing in a logarithmic fashion. And the larger the n, the smaller the bias is going to be, and it's decreasing with 1 over root n rate. What do you think if the mu's are not the same? Is the bias going to be different, smaller or larger? So let's say, okay, let's think about some special case, right? So let's say you have one special case, mu star is equal to mu1 to mu of k minus 1, and mu k is like far beyond. And here is your 1 over root n. So this difference between the best value and this other guy is just much larger than 1 over root n. How does this behave? Is the bias going to be the same, smaller, or larger? Okay, who says it's larger? You say it's larger? Okay, who says it's smaller? Who says it's the same? Okay. A lot of people are just silent. You have to vote. It's democracy. It's a forced democracy. Okay, let's do it again. Who says the bias is larger? Everyone needs to vote. Come on. Is the question clear, or do you want to ask questions about the question? Huh? I can repeat the question, yeah. So previously, all the means were the same, and we analyzed how big the bias is going to be. And we see that's how big the bias is, 2 square root log k divided by n. That's the bias. That's the size of the bias. Now I change the situation. One of the means is lagging behind. The others are all together, and they take on the same value, and that's the maximum value. So we have k minus 1, who have the same value, the maximum value. One is lagging behind. I kind of took away one. And it is actually quite separated from the rest. Like it's lagging behind quite a bit. So what do you think? Is the bias going to be larger? Okay, who votes on larger? Final votes. Okay. It's larger. Larger. Okay, 1, 2, 3, maybe 4. Who says it's smaller? 1, 2. Okay, like, are you gonna say everyone else is the same? Okay, I assume you say that it's the same, but then you have to defend it. So whoever didn't vote on smaller, larger might be picked, then you need to defend your opinion. Do you want to vote again? Okay. All right, so people are a little bit undeterminate, but okay, so let me change the situation a little bit more. So we have half of the guys here in this upper bunch and half of the guys in the lower bunch. So there's two clusters. So now we have half as many as before at mu star, and all the rest is just like in this other group, which is lagging behind. Is the bias going to be larger? Who votes in this case that the bias is going to be larger? All right. Who says the bias is going to be smaller? Okay. Right. So who is the brave soul who is going to explain why the bias is going to be larger? First, I want to hear that explanation. Anyone? Ah.
Essentially, as if you had just K minus all that group in that bunch.
K half.
As if
Yeah.
your N was small.
What happened to N? I didn't change N. I changed maybe K.
Yeah, but you're taking values that are maximized, right? So that are within that group since they're further up.
Yeah.
So every
True.
single time, if you take a bigger value, then it's going to take that maximum value further up. So it's as if
Further up compared to here, I was, okay, so let's say here, I had all the means are the same. Let's say K is 10. So I need to have 10 of these dots here. Whereas there, I have the same figure, except that I only have 5 dots. So there were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then here I have 5. And I'm taking the max. I have 5 here too. I'm taking the max. So now.
Okay, so I will go with the answer invariant, like it's same. Like I'm not defending that it's going to be larger, but I think it's going to be the same bias because the max operation is kind of invariant. Even if you had just one there and all the K minus 1 samples on the left, assuming, the max operation will only
choose the same value,
same max value,
right?
Is what my intuition is thinking. But if I had more distribution on the right, kind of in the sense, then there'll be a little bit more bias. But that's kind of why I'm saying it's invariant. But I'm not sure how, statistically speaking, how well that is correct.
Interesting. I think that what you're saying, that you expect it's really interesting. Well, you're pointing out that the maximum value is kind of the maximum value. But can't we just think about that situation like this, except that here, from this group, I first create these 10 dots, and then I remove 5 of them and put them here. So those 5 are not playing a role anymore. They don't really have a chance of being the maximum. So now the maximum is going to be impacted potentially when I move from this picture to that picture.
But they're kind of disjoint to each other, right? Whatever the
Exactly.
Guess, there'll be a little bit in that error if like the maximum that like the 10th point was there was removed in the sense, and like the 9th point was kept there. But I guess it depends on how many K it grows. So probably I don't know. Like,
so these are random, right?
Yeah, exactly.
So
be random.
But then we take the expectation. So we have to think about, okay, like how does this work?
Yeah, I'm not sure much.
Okay. So who was on the other opinion that it's going, the bias is going to be smaller? Okay, Schwa. Okay. Right. So you're considering the special case when k equals 2, and the means are very much separated. So now you have one sample from the distribution on the right, one sample from the distribution on the left. You take the max of the two. Effectively, you're almost always going to choose just one sample from the distribution on the right. And if we just did that explicitly, how big the bias of that would be? It's 0. It doesn't have any bias. So in this special case, when k equals 2, then we see that, okay, like there must be a big difference. And then you can kind of adjust your expectation, and it's the same thing. It's like, imagine that I first sample 5 guys from here, and then I start to sample from here and update the max. If it comes, any of these guys comes above any of the values here. If I move this very, very far, there is no chance that that's going to happen because I'm only sampling 5 guys. It's a very, very small chance. So I'm not going to modify the maximum value that I calculated by first just choosing this distribution. And so effectively, the bias is expected in this big separation to be as large as the bias would be if you knew that you're only sampling these guys, but only k over 2 of them. But we are only sampling k over 2 of these. So that means it's a smaller bias, because here we saw that the bias increases with k, right? So the bias in this situation is expected to be, yes, it's the same formula, except that need to change this to k over 2. Of course, if I push these guys closer to each other, then it's going to melt, and like you get back the original bias eventually in a continuous fashion. Okay. Right, so this is the bias. If n is not too large compared to log k, then maybe you should be worried about this bias. Larger number of actions, but notice that we have a log k versus n comparison. So log is like compressing the values a lot. So an exponential gap between the two. But let's say that's the case. So it's n is very small, k is very large. We are worried about the bias. What would be a way of reducing the bias? So the proposal in this double Q learning approach is to reduce the bias by splitting the sample. So here, if we had n observations, you will take the first n½ observations and create a sample mean from that. Let's say n is even, so this is not a problem. And then you create another, like you take the second half, and you take the average over those guys too. Okay. Then the proposal is that let's choose the maximizer based on the first half of the sample. So we choose which arm looks the best based on, just half of the samples. And as an estimate, of the maximum value, let's use the second sample. Okay. So the observation is that in this estimate, there are two things that are going on. You're choosing which arm looks the best, which action looks the best, and then you're returning the mean of that. Your best guess of like which arm is the best is, like what else would you base it on than the sample mean? So you calculate the sample mean, but the problem is that the same sample mean is used to actually estimate the value. So if you choose, you have a good guess, maybe you use half of the samples for which arm is the best, then just imagine you're sampling more from that arm to get the mean value for that. Then therefore, you're going to remove a large part of the bias. Okay? So the bias of this is going to be reduced. Ideally, compared to not doing this. Okay. So what's the relationship to Q-learning? In Q-learning, we also have this update, which is using bootstrapping. And in this bootstrapping update, we are trying to get the estimate of the maximum of the action values, where the action values are calculated with some estimation method itself, which is kind of noisy. You can think about it as like it's like as if it was a Gaussian distributed random variable around the mean. Maybe it already has some bias that's kind of not even good. And you just use that sampled value, and then we were just taking the max over those. So that's very similar to the first estimator here, which is just taking the max of these random sample averages. So in Q-learning, the same thing is happening. So the idea then was to mitigate this bias a little bit by recycling this idea of splitting the sample into two. Use one half of the sample to choose which action gives you the maximum value, and choose the other half of the sample to return an estimate for the value of that action that was chosen based on the first half of the sample. Okay? So what's the update equation for all of this? So the Q-learning update equation is going to be, you're at ST, AT, take the odd value, and blend to the odd value, bootstrapped new target. So here is the infamous max. And these are like averages or whatnot. It's similar to the previous setting. So now what we're going to do is that we're going to have two of these functions. They're indexed by I. And in every time step, you're going to choose one of them. And you're updating that one. But you remove this max here. And you replace it with the action, which is greedy. Okay, let's call it, introduce some notation for that with respect to the other function. At this state st plus 1. Okay, so it is either 0 or 1. So this is just a tricky thing to write that. Okay, 1 minus, if it was 1, then 1 minus it is 0. If it was 0, then 1 minus it is 1. Just a short way of writing things. And this greedy action with respect to some q function at some state is just a maximizing action. It's just a notation for the greedy action. Could have written the whole thing there, but maybe it's going to be useful to have this. Okay, so this is the greedy action. Let's say ties are broken in some arbitrary way. Okay. So that's double Q learning. Should be found there from the book. So when we were talking about the bias, we were pretty explicit about that this bias is positive, right? So the estimates of the mean are above the mean. It's an optimistic estimation. And here we're going to work really hard to remove this optimism. If you hear this, what comes to mind? We're working hard to remove optimism. Is optimism bad? Isn't that a bit confusing? Earlier we learned that optimism is not bad. When is optimism not bad? For what purpose did we use optimism, or optimism was recommended? Yeah? Exploration, that's right. So optimism should be really helpful for exploration. How big was the bonus from UCB? You remember UCB, the bandit algorithm? It's like, takes the empirical mean, adds a little bonus, then calculates this index for all the arms and takes the arm which maximizes the index. How big was the bonus, roughly? How large is that? Yeah, it's like 1 over root n. Okay, so we have some free bonus here. We're going to remove it. Is this going to be wise? So when would you want to remove the bias? So in exploration, I wouldn't want to remove it. That's right. If you really care about honestly knowing the values, for example, here is a use case for when this might be needed. You stop exploration. You stop because you exhausted your budget of like how many steps you can go. And at point, you want to return a policy that will be deployed with no further learning. Then you don't want biases, because the bias, the optimistic bias, would be helping with exploration, but you're not planning any further learning. So that would return a bad policy potentially. You don't want that. I'm not following. Which random variables whose means are the same? Common mean, yes.
When you pick the max, it's not a bad action. Right? You go the best. That's all you need. The policy is still optimal in that sense.
Okay, so here we go back to the question. Okay, yeah, let's think about this. Yeah, that might be a very good point. So if we're splitting the sample, yeah, we're splitting the sample this way, and then we choose this action, and this would be the recommended action maybe. Then is this going to be a good action to pick? Better action than if we used all the samples, calculated the averages, and just recommended that action? Who thinks that it is better to do this than what previously we were doing, which is just, yeah, take all the samples, compute the sample means, and take the maximizing action? Which one is better in terms of the quality of the action chosen? The old one is better. So more samples, we are basing the decision on more samples. So even in that case, we are winning. That's okay. So what's going on? When do you want to remove this bias at all? Yeah. I don't know. You tell me, what is cross-validation?
Like splitting the value, like the data you getting from the validated model to that learning.
Right. Yeah, it is. It feels similar, right? Like in cross-validation, people are also splitting the sample. Yeah, but
that at least goes through all these. Depends on the cross-validation method you use. Like, unless you're doing just like a random subset, when cross-validation you're doing like 6-fold or something, you still go through all the partition of the subset. So you still see the remaining n/2 samples, like in our case. Here we don't even see them at all. So in the case that in the first n/2 sample, you only see like very small rewards for like the best maximizing action, but the last n2, like there's probably like, it depends on the scenario, but there's extreme cases. The first n2 sample you get very small rewards, and the last n/2 you get really pushing the reward. That's kind of why the old one is better, because you see.
Okay.
This is what my.
Yeah, true that cross-validation somehow has many faults. It goes through all the faults, and it's kind of thoroughly looking through how many times one method wins over the other or something, in terms of some losses. So what would be that corresponds to that in our case? Let's say we are back to bandits. So up to now, we had 2 faults. So let's say we have 2 faults. What would be the cross-validation way of doing things?
Let's go to the n by 2 samples of the value, like I guess, kind of getting the expected values as kind of a metric already on its own. Then you do the other n by 2 samples, you get another metric, and then wait. Okay, depends on the method used, but then you compare which one is kind of. Yeah, I guess it depends.
Yeah, I guess like we would like maybe one way of making an analog to cross-validation, that in cross-validation usually used for model selection is, you know, you have a number of different models, and you want to know which one is doing best, like they differ in architecture or whatnot. So what's the analog to that here? Just the arms, just the actions. We want to know which one is doing better. And then you do these faults. You train on some of the faults and evaluate on the rest. What the heck does that correspond to here? What's training? Well, isn't that the evaluation? I'm confused. Yeah, I think that like there is no very clear analog here in a way, because there is almost no training. If you want, maybe the training would be calculating the sample means, but then what is evaluation? Oh, and then seeing whether that would be winning on the other half of the sample. But no, but we said that we want to train, and okay, so the training means that you're changing something, or like it. In this case, it's like you just have the arms, and then there is nothing to be done about that. So it's kind of like I don't know, like almost works, but I don't quite know how to make that work. But how could we use? How could we make use of both samples? Both halves. We could merge all of them, take the grand mean. Then we are back to this. Back to the original method, to the odd method, in terms of selecting the best action. Anyway, so in double Q learning, that's kind of what they do. So they calculate these 2 Q values, and then when it comes to recommending actions, you just sum up the 2 action value function, because you want to use all the samples. And somehow you kind of reduce the bias a little bit along the way. And then eventually you're using the same number of samples, kind of almost. And then you expect this to work a little bit better. It's a very nuanced thing. It's not that obvious that it should be working better. And when it comes to exploration, I have serious doubts that this is doing anything good for us. Okay, we didn't even make close to answering this question, which is a tiny little worksheet question. But I think maybe there are interesting things to be learned about this double Q learning, and all this thinking about how you should be designing these algorithms, what to consider. So good. Next time, we already have the double Q learning equation on the board. We're going to start with that, and then we make our way through the rest of the question. Of course, when you would be solving this at home, you would just start with that, and then you wouldn't the thinking that we're doing is supposed to happen when you are reading these things, right? Like you're reading about double Q learning. Why is this happening? Why are they doing this thing? All right, okay. Have a good weekend.